Hi, this is Raed Alsurdeh. This is the presentation for the paper titled "The Hybrid Workflow Provisioning and Scheduling in Cooperative Edge Cloud Computing, accepted on CCGrid 2021." The presentation will go through the following: the advancements in IoT industry and applications, conceptual definition of a hybrid workflow model, the main motivations and contributions, then discuss the cooperative edge cloud system model and its main components. Next, the hybrid workflow scheduling for both resource estimation and task allocation. The main experimental results will be highlighted. And finally, the summarization of the paper conclusions and some future work direction will be provided. In simple words, the Internet of Things, or IoT, refers to a system of interrelated, internet-connected objects that can collect and transfer data over a wireless network without human intervention. There are many enabling technologies for IoT. These include wireless sensing networks, embedded systems, short-term and long-term networking protocols, and many other technologies. Recently, IoT industry demonstrated a huge advancement at infrastructure and application level. It has been involved in a wide range of applications areas, such as manufacturing, supply chain management, transportation, healthcare, and many more. So the enormous number of connected devices bring to the surface many challenges for securing generated data, processing it at real time or even near real time manner. And the important here is managing the shared resources that hosting IoT applications. An example of shared resource model is in smart cities, as we can see on the next slide. Smart cities use IoT devices such as connected sensors, lights, and meters to collect and analyze data. The cities then can use this data to improve infrastructure, public utilities, and services, and more. As we can see from the figure, the complexity of managing the variations of applications in terms of type of data, models, and the interaction with other applications or systems. In common, computation models can be categorized as stream processing with or without real processing constraints, batch processing for cumulative data processing, and mini batches processing for intermediate data processing with some level of interactivity. However, it can be clearly stated that any of these applications need to work on the top of hybrid model of mentioned processing models. This is the main motivation of hybrid workflow. A hybrid workflow, we define a hybrid workflow as integration between stream and batch processing models. Managing the execution of hybrid models can be challenging to meet the variation in computation constraints of each integrated model. At large-scale applications, managing the computation and data dependency in a unified model and in shared resources can be complex to meet quality of service-based execution at hybrid workflow or application level. In this paper, we formulated this problem as three sub-problems. First, the hybrid workflow modeling, then resource estimation and task scheduling. The terms task and application are used interchangeably in this presentation. So let's move to the hybrid workflow model. A stream task represents a set of processing operators in a certain stream execution pipeline. The execution of a stream task is modeled as a MGC queuing system. We assume a Poisson distribution for the incoming data streams and a general distribution for the service time at the computation server, which can be a cloud server or an edge server. Based on this formulation, the estimated number of servers is calculated based on the arrival rate, lambda, and the service rate, mu, and under system utilization constraint, as known in any queuing system. For batch task, we assume a deterministic mathematical model to compute the number of servers. The batch task modeling strongly considers the contribution of total amount of data received at the computation system. So based on what we mentioned, the hybrid workflow scheduling is a multi-objective optimization problem of monetary cost and execution under the constraint of execution deadline and throughput. The literature search shows an intensive work on resource provisioning and task scheduling in cloud and edge cloud system. However, we noticed limited effort to employ the cooperative edge cloud to resolve the hybrid workflow issues. The main contribution of this work can be mentioned as an adaptive resource estimation algorithm based on gradient descent search technique and an online approximation for an unprofiled hybrid workflow. In fact, in previous research, we investigated the gradient descent based resource estimation. In this work, we provided an enhanced version to handle uncertain and unprofiled hybrid workflow in which the execution time, the execution function, is unknown in advance. The second contribution is a cluster-based or group-based resource provisioning and scheduling algorithm for hybrid workflows in a cooperative edge cloud computing environment. Lastly, we provided a comprehensive performance analysis of edge cooperation on reducing workflow execution time and cost. The cooperative edge cloud is an integrated computing model utilized to run complex applications such as real-time data analytics, visual guiding services using wearable cameras, on-demand gaming, and real-time video streaming. The cooperative model incorporates three main layers: IoT, which includes sensing devices. We assume no computation at this layer. The cooperative edge with two types of resources: the edge devices and the edge data centers, and the multi-cloud layer. The cooperative schema considered in this paper is described as a three-tier vertical cooperation between edge devices, edge data centers, and multi-cloud computing services, and also a horizontal cooperation within the edge layer between the edge devices and the edge data centers. The model does not consider any level of horizontal cooperation at the multi-cloud layer. The cooperation is utilized for both computation and data storage. The resource estimation, which is the first step in the hybrid workflow scheduling, is a multi-objective optimization problem of minimizing the joint of total workflow execution time and the total number of computation units or servers. The desired outcome of the resource estimator is a group-based workflow execution plan, which can simplify the provisioning and scheduling in a desired computing system. The figure shows the resource estimation use gradient descent technique. The gradient descent is a method to find a minimum of an objective function. In this case, is the workflow execution function, with parameters through updating the parameters in the opposite direction of the gradient of the objective function. So for each stream task, 3 parameters are considered: the arrival rate, lambda, or stream arrival rate, the window size, omega, the time length of the stream collection, and the throughput, which is the percentage of data to be processed. The idea of adopting parameters, the idea of adopting gradient descent is parameter tuning to achieve the objective function minimum at a workflow level. Thus, the input of estimation process is an array of configuration parameters for each stream task, including the arrival rate, window size, and the throughput. So at the end of the outcome of the estimation output is the tuned configuration that minimize the workflow execution time and number of computation units. The proposed estimation process relies on an offline gradient-based optimization, which assumed a prior knowledge of the workflow execution time. This refers to a batch gradient descent algorithm, as all data points are evaluated and no approximation is carried out. That's the assumption from our previous research. However, this assumption limits the application to only profiled workflows in which the execution function is already known and the structure is already known. However, to attain more generic estimation approach for hybrid workflows, this technique is extended to address an online approximation mode. To achieve this objective, we relied on 2 assumptions. To validate this technique. The first thing is that the workflow cost function is a continuous and a differentiable at every point in the parameter domain with no bend and discontinuity. And according to this term, the differentiability, the execution function can be approximated locally by linear functions. Algorithm 1 shows the gradient approximation steps. So the cluster-based cooperative hybrid workflow provision and scheduling includes 3 steps. Firstly, fetching the current status of edge nodes, and this includes resource availability, networking performance, and connectivity with other computation nodes. Secondly, producing execution strategies for workflow groups to enhance edge resources utilization and reduce data communication between edge devices and data centers. And finally, do the scheduling at the group level and find the best execution strategy that jointly optimize the execution time and the monetary cost for running all workflow groups. This slide shows the group-based scheduling modeling to compute the execution time and cost. The input for these functions in equations 14 and 15 is the tuned configuration array from the estimation step, and the transfer time and transfer cost in equations 16, 15, and 17 is based on the bandwidth and the amount of data transferred among the group tasks. The bandwidth value gathered at resource discovery step. Please, for further details, refer to the paper. The algorithm to compute the execution time and cost based on a given allocation strategy is provided in algorithm 3. However, an allocation strategy is a set of edge and cloud resources that are available and can accomplish the requirement of execution and a research or an execution group. So let's move to the experimental section. The objective of the experiments, which we will discuss later, is to evaluate the contribution of edge cooperation on reducing the execution time and monetary cost to executing hybrid workflows. We assume three resource models. The first one is a cooperative edge cloud, in which edge resources work collaboratively by sharing and exchanging computation and data workloads. The second is the non-cooperative edge cloud, in which computation or storage collaboration is not assumed in both sides, in vertical and horizontal. Extra computation and workloads are sent direct to the cloud in case of edge devices are not able to process the incoming data from IoT devices. The third one is the public cloud or the cloud-only resource model, where all executions will be sent to the cloud and there's no contribution to the edge at this scenario. Moreover, to incorporate a hybrid workflow complexity, three models are provided: small, medium, and large, which are different in number of tasks and scalability mode. The first experiment to evaluate edge cooperation under the variation of three model parameters, which are the window size, the arrival rate, and the throughput. So again, the window size is the time to collect data, arrival rate is the stream arrival rate, and the throughput is the percentage of data to be processed. The main challenge of window size, the first case, is the increase in the window size, is the increased amount of captured data. This challenges the scheduler to handle the cumulative collected data from IoT devices. Here, we assume that stream processing is allocated to each devices for the sake of reducing streams collection delay from IoT devices, and to benefit also from the non-stationary advantage for high data collection conversion. However, each devices are limited in the computation and the storage capability. Figure 3 highlights the disadvantage of the cooperative scenario when applied for complex and large-scale workflow structure. The cooperative scenario produced a significant time and cost saving of up to 50% and 85% compared to the non-cooperative scenario. Respectively, the impact of network overhead with large data transfer explain the poor performance of non-cooperative scenario in optimizing hybrid workflow execution. In case of arrival rate, figures 4 and 5 show the result of comparing the responsiveness of the three models to variation in stream arrival rate for the third workflow structure. The arrival rate has a direct relation to the amount or to the number of servers cores in queuing system to keep system utilization at acceptable level. For an arrival rate less than 100%, the scheduler was able to control the execution time and cost because the stream tasks are provisioned as a group. The cooperative-based system distributes the growing workload with a 50% cost increase. This demonstrates the cooperative model ability to utilize edge resources without migrating computation and data workload to the cloud. In case of throughput, figure 6, 7, and 8 show the impact of throughput variation on three workflow structures. One conclusion is that the scheduler must adjust arrival rate and window size parameter to achieve a minimum throughput. Meanwhile, a high throughput incur additional time and cost with the cloud-only system. Figure 8 Figure 8 shows that for large-scale applications which require processing high proportion of data, the cooperative model outperform other resource models in minimizing the time and cost. This is related to the efficient usage of the allocated resources without provisioning additional resources. The second experiment is to evaluate the edge cloud cooperation on reducing data transfer and cost. The main motivation of using the cooperative edge is to allow cooperation between edge resources to reduce the amount of data and computation workload sent to the cloud. Figure 9 shows the result of running a large hybrid workflow with varying window size in the cooperative and non-cooperative edge cloud system with respect to the data transfer time and cost. Results show that cooperative model significantly reduce data transfer time and cost with long-term data acquisition as the window size increases. To conclude, the align gradient approximation is a visible technique to resolve estimation issues of uncertain and unprofiled workflows. Also, the cooperation schema assumes horizontal workload and data migration among data nodes under the constraint of application data dependency and the cooperation status for these nodes. Experimental results show that the cooperative model outperforms the non-cooperative and the cloud-only model at critical points like high arrival rate and throughput. Also, it can efficiently reduce the time and cost of migrating data to the cloud. For a future work, more advanced statistical methods and learning algorithms can be utilized to improve resource estimation and performance. Thank you for listening. Please feel free to ask questions by leaving a comment on the YouTube video or sending direct email to my email as shown. Thank you.